All right. 12, 5, number 4.
Yeah, it's they only give you like x equals for it, and then you're doing the triple integral. So I just wanted to see the process and which one you would select
All
to
right.
do as your inner, middle, and outer integral.
It's going to be a paraboloid. So it's triple integral x dv. Let me copy it down. The region is a paraboloid x equals 10y squared plus 10z squared, and x is equal to 10. Okay. And you want to set this up. And what I'm going to do, I'll do it the regular way. Let me get this going there. There we go. The old-fashioned way of just trying to figure it out by drawing it. Um, it's going to be a paraboloid. If I draw it in the traditional XYZ axis system, it's going to be a paraboloid that opens up kind of this way. It's not the best picture, but okay, it's opening up in the X direction. Does that make sense?
Let me pin your camera.
So it's got a point at the origin, and from there it grows.
Okay.
And then X equals 10, if I just kind of say that's 10, that's a plane. And that basically stops the paraboloid. So it's basically a paraboloid that just simply ends. What you can do if you wanted to is you could set these equal to each other. This will help us with our bounds. Uh, so set x equal to 10, and then you just divide it out by 10, and that tells us what our region of integration is. So back here on the xy, I'm sorry, on the yz axis, you have the circle of radius 1. So this will help us with our bounds. I'd like to take a moment here and do this on Desmos because I think it's kind of fun. Um, I'll come back to this, of course. Let me get Desmos going, and I'll share the screen. If you go to the 3D Desmos, I'm going to type in x equals 10y squared plus 10z squared. Now, on the next line, what I'm going to type in is x equals 10. I need to actually uh, scale out for that. Extended 3D, that's what I want. There we go. Okay, I want to show you a neat little trick. Watch this. On the first bound, I want to limit, it's going to be x between 0 and 10, so I'm going to use my squiggly equals, and I'm going to write x less than 10. And on this bound here, let's see if it works. I'm going to try it out. Haha, it worked. All right, you see that?
Yes.
Isn't that cool?
Yeah. That makes it so much easier to look at the picture because sometimes you're looking at them and they're not um like it's not clear where it cuts it out, and when I'm trying to rotate it around and stuff, it's like I'm not good with the 3D visual representation in my head, and sometimes it confuses me more when I'm looking at it and Desmos trying to figure out like what it is. So I will make note of those where you can put the bounds for each equation
It,
after
take,
you write the equation.
it takes a little bit of just kind of goofing around with it. Oops, I didn't mean to do that. That's a much more satisfying picture.
Yes.
Um, that's your region right there. So again, the way you do it is you type in the bounds the normal way, and then you have to actually kind of go back to each bound and refer to the other bound, and you have to create these inequalities. Now, this is kind of an imperfect science. The best thing I've learned to do is just keep trying until it works. And
Okay.
so it's fun to play with. And then I went to this wrench here and I played with the bounds on the Y and Z just so that we would have a little bit of a little clearer picture here. So that's what it looks like. It looks like one of these things. Okay. All right. So I'm going to stop the share here. I can always come back to it if you need me to.
Okay.
So my question to you is, you have this dV right here, but you'll notice that your Y and Z variables make a circle. That should be a big hint. What do we want to do with the Y and Z bounds?
With
Because
the Y.
integrating over, what's that?
I'm sorry, keep going.
Well, the Y and Z bounds create a circle, and that's a big hint in terms of how you set this integral up. If
Okay.
you if you try to integrate it in rectangular coordinates, you've got some challenging integrals because you're going to be dealing with square roots.
Yeah, so that's how I was doing it. I was doing like z squared minus one and the square, the square root of z squared minus one negative, and then the positive square root of z squared minus one for y bounds. But then and then so for z, I guess it would be from negative one to one.
Yeah, but then you got to integrate that stuff, and that's where you're going to run into some real challenges. So anytime you see a circle as part of your integration, you should immediately be thinking of r and theta.
Okay.
So we're going to trade y and z out for r and theta. And I just look at my picture here, and I can tell you that the r is between 0 and 1, and the theta is between 0 and 2 pi, because that's what describes the circle back there on the YZ plane. Okay, so I'm trading out y and z for r and theta. And then x will stay x. And so I guess it's a question then of how we want to set up our triple integrals. So I'm going to spread these guys out a little bit. And I'm going to do keep dx. And then where normally I would have y and z, I'm going to have r and theta. And that means I have to include that Jacobian. And I can put
So
it there.
we could separate it out into a Cartesian coordinate for the first one and then the r and theta for the second portions
Yes,
of. Okay.
absolutely. This is called cylindrical coordinates.
Okay.
Anytime two of the variables create circles, those should be traded out for um, um, r and theta.
Okay,
Okay.
so this one I think was the homework before we did the cylindrical like this was the initial homework of just triple integrals. So I thought we were supposed to do this one in the Cartesian coordinates completely because it was prior
Um,
to the cylindrical
I mean, you
homework.
can. Nobody's going to know.
Okay.
Um, so then it's just a question of how do you want to mess around with this. For example, with the r and theta, I can put the bounds on right now.
Which makes it much easier.
And then I just need to tweak the rest of it just to make sure it behaves. So x is the integrand for now, and I'm just going to keep it as x because it agrees with this. And now, normally what I would do is I would draw an arrow in the x direction, and it enters through the paraboloid, which I'll temporarily write as this, but I'm going to change that in about 2 seconds, and it exits out 10. Now, this is not quite correct because I've got too many variables. I would immediately trade out. So coming back to here, factor out of 10, you get y squared plus z squared, and that's actually r squared, 10r squared. So this is actually 10r squared. Okay.
Yes, that makes sense.
So now you've got yourself an integral that's going to work out dandy. You're going to integrate the x as usual, 1 half x squared. And you're plugging in 10 and 10r squared. When you plug in 10, you get 100 over 2 is 50. When you plug in 10r squared, you get 150 r to the fourth. We're done with the x part. We're done with the inside
Yeah.
integral. And again, I'll pause here for any questions. Does that make sense?
Yes, that makes sense. And then you can factor out the 50. So then we'd have 50. Oh, okay.
But
51.
also, yeah, you're true. You can factor out the 50, or you can leave it
And
alone. Doesn't matter.
okay.
But what happens next is that when you come down to the next integral with r, this extra r, the Jacobian, is going to feed through. Don't forget them. So now you're going to do the r integral, and it's going to be integral from 0 to 1. So it's going to be 50. Let me just write it 0 to 1. I'll put the 50 out in front. This r comes through here, makes r minus r to the 5 dr. And that's not that bad, especially when our bounds are 0 and 1. Uh, 1 half minus 1 over 6, that's going to be 1/3. So 50 over 3. And then the rest of the problem is just integrate from the theta parts. That's just going to be 50 over 3 integral 0 to 2 pi d theta, which is just going to be 2 pi. So it's going to be 100 pi over 3. So the 50 times 2, and that should be your answer.
Perfect. Okay. Yes, that makes much more sense. And it's
So again, any questions on setup?
no, that was much easier using the cylindrical coordinates. And then
Yeah.
um the other either one, 8 or 9, that's where we're setting it up like all 6 different ways.
All right.
Um
Let me
I
go to it.
I was getting the equations right, but for it's like two
Oh
or three of
Lord.
them. I'm still doing the thing with the bounds where
All
I
right.
was the first bound, the inner bounds and the outer bounds, right? But then I'll like mix up the order of the middle bounds.
Let's look at number 8.
Okay.
First order of business is to make sure you got a clear understanding of what the picture looks like.
Okay.
So really, they don't even give us an integrand. It's just generic fxyz. So the bounds are z equals 0, x equals 0, z equals y minus 8x, and y equals 16. Okay. Now, let me if I try to do this the traditional way, I could probably get a little bit into it. Let's see. Z equals 0 is the xy plane, so that's one bound. X equals 0 is the yz plane, so that's another bound. So those are bounds right there. Everything's going to be on this side of those two planes. Um, y equals 16
So
is
why does y equals 0 become the you said that that's on the XY bound, or I'm sorry, it's hard to read it's kind of blurry. So why are those on those specific planes and like, because Z would equal 0 where it's coming out at X. at X
It's
just as well as it would for Y, right?
every
So that's
point, it's basically every point that has zero as a z coordinate. So all the
okay.
points in the xy plane are really just x comma y comma zero.
Okay.
And this is gonna these points are gonna be zero comma y comma z.
Okay. I think that that's what because there were a lot of them where like it was zero was supposed to be the bottom, but I was putting an equation that might yield an answer that was less than zero.
All right. We know that y equals 16 is a plane, and I've drawn it in like this, and then we got the z equals y minus 8x. And, all right, let's see if we can figure that out. That's going to be that's going to be an interesting one. One way to do it is to like if x is zero, z is then equal to y, so we have um, basically a 45-degree line. That's on the x equals zero, so that's on the yz plane. And then if y is zero, z is negative 8x. And that gets a little interesting to see here. Z is negative 8x. It actually is coming back here. Hold on. No, hold on. Z equals negative 8x. If y is zero, well, I'm back here, my bad. Um, I'm actually down. Z equals negative 8x. It's actually back here. Yeah, it's going to look something like this. And this gets a little tricky to see. Um, so you know what I'm going to do? I'm already kind of confusing myself with my picture here. So I'm going to give up and I'm going to go to
Okay.
Desmos. So let me go to Desmos. And you're going to get Desmos on the test. So you can always set them up that way. Um, so let me shares at Desmos. Let me get rid of these guys. Let me, I want to be back to the, okay, yeah, I just want to get back to the normal. All right. So what I'm going to do is I'm going to type in z equals zero. And I'm going to type in x equals zero. And now what I'm going to do is I'm immediately go back and say, well, I know it's z equals zero, and I know it's going to be x equals zero. Um, actually, let me just continue on. Let me go to y equals 16, extend to 3D. I need to, there we go. Okay, so now I'm starting to get a picture here. Now I'll go back and I'll tweak things. The third one is the tricky one. Z equals y minus 8x. All right. Do you see that?
Yes.
Now
So are is
it's
ours the enclosed one that's so which one of like so the bounds
well,
would be what's in between the purple and the red above the green and to the right
yeah.
of the okay.
So we're gonna go exactly. So we're gonna have to play with this. This is gonna take a little while. We're gonna goof around. Um, it looks like I'm gonna want to set z greater than zero, and for x, I'm beginning to think it's actually on the less than zero. Let's try it. It's starting to take shape. Oops, I left it off. There we go. Well, I can always come back and fix it. For z equals y minus 8x, it looks like we want to have z is greater than or equal to zero. Let's try x is greater than or equal to zero. Let's try y is less than or equal to 16. Yeah, this one's getting a little tricky here. Like I said, this one, oops, let's try this. I'm trying to get the region here. I can kind of see it. Yeah, okay. I think it's starting to take shape. It's a sliver of a region. For x is equal to 0, that's the YZ plane. That's the purple one. It looks like we want to have, let's try Z be positive. And let's try Z is less than Y minus 8x. Okay, it's starting to take shape. With it's this sliver of the region here. You can kind of see the red outline there. It's going to be this little triangle here. Let's see if I can get that better. Z0. Um, that's the YZ plane. So again, let's try the bound. Z is less than Y minus 8x. Yeah. And then let's see. I want X to be, okay. So the more it's starting to take shape. Gosh darn, I'd really like to get the red and the green kind of done. So let's see if I can do that. It's going to be, maybe, let me try something here.
What happened?
I didn't like that.
Is it because we don't have an X bound yet for the Z part?
No, it's just I haven't figured it out yet.
Okay.
We've got the shape. If you can ignore this
Okay.
big red sheet, the red
Okay.
sheet is the Z, and it's going to be everything. Oh, you know what? It's going to be less than Y. So I finally got it. All right. Oh my
Okay.
gosh. Isn't that cool?
Yes, that's much easier to see, but you all the manipulation of you figuring it out, I can see it on there. I didn't get all of those as you were doing them, but I can see how if you don't do it correctly, it's not at an intersection point.
This
So,
is this is like 99% of the problem right here
yeah.
because it's really difficult to see it otherwise. I'm actually going to copy the picture on my piece of paper as best as I can.
And I was trying to write all of those on my notes, but I wasn't using Desmos to do it. So then if I got like a positive where it should have been a negative or a negative where it should have been a positive, then when I was doing my bounds, they were incorrect in my original equations. Okay.
Let me see if I can click on this. Our job now, that's the picture. Once we've got the picture, it's really, we can set up all 6 bounds pretty easily. First of all, this is a nice region because it's type 1. There's not going to be any ambiguity with the bounds. So we don't need to set up more than one triple integral. And so I'm just trying to get some stuff figured out here. Um, let's see, that's y equals 16. So x would be, looks like 2. Yeah. Yeah, X, this would be 216. That's obviously the origin. So I think we've got enough information. So yeah, you know what? This is like 95, 98% of the work here is just trying to figure this out. And gosh, I don't want to make this sound really confusing, but this is kind of how you do it. You type in the bounds all on their
Yeah,
own,
I
and then you
can
just
see
kind of go
that.
back and play with the using curly brackets, you play with inequalities.
Yeah. And then a lot of those are going to be helpful for when we're setting up our integral, because then if you know that z has to be greater, or it has to be greater than zero and less than y, then zero would be your lower bounds and y would be your upper bounds for one where you're integrating z and y is behind it, right?
Well,
But
yeah, give me a second here. I'm going to go to my overhead. I'm just copying the picture down. Okay. I don't expect, I mean, if you can do this, this is really good because it does help, but I don't have an easy formulaic way to do it. You saw what I did here. I basically had to screw around with it until I got it to work.
yeah.
So, with this one's a little bit of a tricky one, but with some practice, hopefully this helps. I'll tell you what, I'll keep this, I won't take this page down, but I'm going to stop the share here.
Okay.
And I've labeled my region here. I've got y equals 16. This is this face right here. The back face is x equals 0. The floor is z equals 0. And this slanting face is the z equals y minus 8x. So I'll do one of them with you guys. If I do the dz, dy, dx ordering, the dz bounds would be drawing an arrow to come up from the bottom to the top. It would actually enter through the floor and exit out that slanting side here. And then once you're done with z, just look at the xy plane. So these are your z bounds. And then what you do is you look at the region on the xy plane, and that's going to be it's going to be this little sliver here. That was 2 and 16. This was 16. We just need to figure out an equation for this line. And that's just going to be, well, it's going to be y equals 8x. Okay. So if we do dy bounds, y will be between, it enters, you draw your arrow in the y direction, it enters at 8x and exits at 16. Those are your y bounds. And then your x bounds are just whatever it spans. That's 0 to 2. So if you set up your triple integral, those will be your bounds. And then dz, dy, dx.
Okay. The 8x is greater than y is less than 16. So then the y. Okay, so that's because if we had y minus 8x equals 0, then we would add 8x to both sides. So y would equal 8x, and that's the lower bounds. Okay.
Well, okay, right here, this y equals 8x. You can figure it out two ways. I figured out that the corner was 216. That
Mm-hmm.
goes to the origin. Another way to do it is to look at the original plane. And when you're on the xy plane, z is 0. So if you put a
Mm-hmm.
0 in for that z, just then you just scoot the 8x, negative 8x over and get y equals 8x. And then pretty much you just do the same thing for all the other regions. I'll do one more with you guys. How about dx? How about dx, dz, dy? Dx, dz, dy. I'm just making it up.
Okay, so
So for the dx, dz, dy, I draw an arrow in the x direction. It's going to enter through the back. So your x bound, your lower bound for x will be 0. It's going to exit out right here, but I have to solve for x. So it's going to be y minus z over 8.
it's gonna go from
Okay.
0 to y minus z
Now I'm done
over.
with x. And so what I do now is I just draw the YZ shadow. And that's where I have this line, it's actually this triangle back here. And they're going to be meeting up here at 1616. So if I do dz next, I draw an arrow in the z direction, and it's going to enter through the bottom, which is 0. It's going to enter through the top, which is going to be z equals y. And then the y will just be the constants 0 to 16. And those would be your bounds on your triple integral if you did dx, dz, dy.
Perfect.
Does that help?
Yes.
Let me go back to the picture here. Once you've got the picture drawn, you can play with the orientation to see it better. For example, that's the, well, if I look at it straight on from X, that's the, what you see on the YZ plane. If I look at it on straight from the Z, normally I like to get the Y, positive Y on top. That's what you see on the XY plane. So Z equals 0, you're looking straight down. So this is really nifty because you can play with it and get a real sense of the picture. This one was a tricky one because it's a tricky one to graph by hand. This slanting plane is kind of problematic. You can figure it out, but I think having Desmos is nicer.
Yeah, I think that I'll do a lot of practice problems with those and try to see.
The 13 to number 8, find the work done by the force field f of xyz is 4x plus 4y plus 5. So 13 to number 8. And we're going to do the helix, which is r of t is the 7 cos 7 sine and just 2t. We're doing this for 1 at revolution, so 0 to 2 pi. So find the work done by the force field on this particle. And it turns out that work is f dot dr. It's an integral. So it's just um, we have to find dr. So r prime is dr. It's going to be negative 7 sine t, 7 cos t, 2. So then f dot dr second here is just take the dot. So let's see, it's going to be, what do we get? Negative 28. You know what I forgot to do? I forgot to make the exchanges here. So my bad. Okay, hold on. Make sure. Sorry about that. I missed a step. I've got to take my f and convert it into, so we have consistent variable here. So it's going to be, so x is 7 cos t. So this is actually going to be 28 cos t. This is 28 sine t. And that's just 5. There's no z in there, so this stays the same. Now I'm going to dot this with this f dot dr. Let's see, 28 times 7. Geez, let's do this.
196? No?
Yeah, I think you're right. 196. I just want to make sure. Yeah, 196. So it's going to be negative 196. So it's this with this is negative 196 cos t sine t. Ah, we're going to get plus 196 sine t
Those
cos t. So same thing. Plus 10. All right.
are just 10.
Huh. So I guess, yeah, that just cancels out real fast. So zing, zing. You're integrating. So it's 0 to 2 pi 10 dt. So you get 10t 2 pi is 0, so you get 20 pi. All right. All right. Well, we got a little lucky on that one. I think that's the way that one's set up. It's going to always do that in this case. Um, I guess you would say joules, right? All right. Does that make
Um,
sense? Such an Yep. Okay. It's an integral because we're not moving in a straight line. And back in the module 10, which was only not even 3 or 4 weeks ago, but it seems like ages ago, you saw f dot dr as being, I'm sorry, you saw work as being the dot product of two vectors. That's assuming you're moving one in a straight line. In this case, we're obviously moving them in a helix, so we just have to perform an integral. But that's the easy part. All right. Cool. All right. Any other questions?
easiest
So
to
I'm going to
perform.
share the screen. This is 12.7, number 6.
Did I give you the
Use
wrong?
cylindrical coordinates to evaluate this triple integral rad x
Oh,
equals.
that's not. Sorry. Let me see if I wrote down the problem wrong. Because it's, hold, I'll go to, which one did I write down wrong?
Well, you know what? I
Uh,
have 12.6.
okay, yeah, because it
My
should be
bad.
like they give you a list of a bunch of different integrals, and then you're just supposed to select whether it would be best to do Cartesian coordinates, cylindrical coordinates, or
Can you see that okay?
spherical coordinates. Let's see.
Can you see that okay?
Yeah.
All right.
Yes. Okay, that's the one.
You know what? I probably don't need to do this one on a sheet of paper, but I'll just keep it this way. Match the integrals with the type of coordinates which make them the easiest to do. Put the letter of the coordinate system to the left. All right. So let's look at the first one. It's integral 0 to 1, 0 to y squared, 1 over rad x dx dy.
So that would be Cartesian, right?
Yeah, because there's no obvious circular issues going on. You're really looking for circles or spheres.
And then the
Um,
second one then would be spherical because it's a
yeah,
sphere.
absolutely. In fact, this would be this thing right here, x squared plus y squared plus z squared less than or equal to 4 is actually a full ball. It's a filled in sphere of radius 2. And then this just tells you the next three bounds just tell you that you're working in the first octant.
Okay.
Okay. And this would
Regular.
definitely be spherical. Make it a
Okay.
lot easier for you. Uh, for the third one, uh, x is just between 1 and 2, y is between 3 and 4, z is between 5 and 6.
That Cartesian too?
Yeah, because that's a rectangle. That's a rectangular solid. That's a box. So it's a cube actually.
Oh,
For number 4, um, right here, 1 is less than or equal to x squared plus y squared is less than or equal to 2. X squared plus y squared is going to create a circle. And so this is actually a ring. Okay, it's everything. It's above radius 1 and less than radius rad 2. So this region right here creates a ring. Z is just Z. you would trade out x and y for r and theta. This would be cylindrical.
Okay.
So you would actually leave you would actually set this up as a dz and then an r dr d theta integral because you're going to trade out the x and the y for r and theta. Make sure you include that r for the Jacobian. But when you integrate, your first integral is going to be a dz integral, so that's just going to be 1/3 z cubed. And then you just plug in the bound. So it's actually not too bad. And then this guy right here, double integral 1 over rad x squared plus y squared, where d is it's a circle less of radius less than radius 2. So definitely want to do this is just a double integral, so we go polar.
Okay. So that's another one of the telltale signs where we would do polar because it's the double. But if it was a triple integral where we had z somewhere in there, then that would be a cylindrical coordinate, right? As long as it wasn't a sphere. No?
So
How?
polar is really only in R2, but
Okay.
when you're in R3 and you're not dealing with spheres, but you are dealing with circles, that's cylindrical.
Okay.
So cylindrical is really just polar in R3. They're very closely related.
Got it. Okay. That
I'm going to go ahead and stop the share. Any last questions on this one?
no.
All right.
Then let me see what the other ones that I have.
We got time for maybe one more. Any last questions?
Let's see. I had
So I'm going to go back to the share. 12-7, number 13. Here's your region of integration. It's a cone. The angle of the vertex is 2 pi over 3. The top is flat and a height of 1 over rad 3. We're going to create the limits for Cartesian, cylindrical, and spherical. All right, let's do it. Let me draw a picture here. So let me get this translated down to here. This is again, this is 12-7, number 13. And then let's see, the angle at the vertex is 2 pi over 3. And we're told the height is 1 over rad 3. Okay, I think I got enough information here. All right. We need to figure out the equation of this cone. A cone is going to be z equals some value of a times square root of x squared plus y squared. Okay. And so what I need to do is just kind of, I suppose I could, I'm looking at this, I could probably figure this out just using trig. Let's do this. Yeah, that's what I'm going to do. I'm going to go with the x and the z. So if I just plot it with x and z, then I basically get a triangle. And half of 2 pi over 3 is going to be pi over 3. So that means this is pi over 6. You've got to be careful there. And this tells us that I don't know what the x is, but I know that the height is 1 over rad 3. Now, this is actually a familiar value, but basically, if I don't know what x is, so I'll tell you what I'll do. I'll do it the old-fashioned way. I know that z is 1 over rad 3, and I know the angle is pi over 6. So since I've got opposite and adjacent, what I'll do is I'll say tan of pi over 6 is going to be the 1 over rad 3 over x. And that way I can figure out x. X is going to be, just by cross multiplying, it's going to be 1 over rad 3 and then tan of pi over 6. Now that's an angle you should know. if not, I mean, if you draw out that table, it should be one
Pi
over
over.
rad three, actually. I'm gonna double check that.
Pi over
So
6.
tan of pi over six, even I forget.
1 over. So it's 1/2 and 2
Yep,
over.
it is. All right, cool. So x is one. Yay. All right, so that gives us a lot of good information here. That tells us that this is one. Cool. So if I set this up in Cartesian, I'll be lazy here. I'll just do dz dy dx. In fact, I forget, does the original integral,
It doesn't say you
oh,
have to do them in a specific order. It just says
so
that you have.
let's just go
Yeah.
dz dy dx. So that means if I draw an arrow in the z direction, it's going to hit the cone. Oh, you know what I need to do? I just need to figure out what this a value is. Um, so what I'll do is I'll use this point that I was already playing with. It was one, x was one, y was zero, and then z was one over rad three. So what I'll do is if x is one and z is one over rad three, that means a is one over rad three. So the cone here is that. It looks ugly, but that'll do the job. So we actually enter through this cone and we exit out the top, which is the one over rad three. The dy and the dx is just a circle of radius one. So that would just be your x squared plus y squared is one. So I would do negative rad, it would be one minus x squared, and then positive rad, one minus x squared, and then negative one to one for my x bounds. That would be the Cartesian.
Okay.
And that
And
will
we
tell you right now that that's going to be a nightmare because of all those square roots. So if we do polar cylindrical, my bad. Um, the two variables that are making the circles are the x and the y. So I'm going to trade them out. I'm going to leave the z alone, just like that. My I can my picture, my r and theta just make a circle of radius one. So that's beautiful. I've already got my bounds figured out for r and theta. The z bounds, well, I would just basically, I'm going to goof off with this stuff right here. X squared plus y squared is r squared. Square root of that is just r. So you just have 1 over rad 3 times r, the whole thing times r. And then just this doesn't change. So that's your integral for cylindrical. So far, so good.
Yes.
Okay. Now that one would be workable. I don't even think we have a function there, do we?
No, they didn't get
All right.
no, they did not. We don't have to work them out. We're just
All
we're
right.
just setting up the
Now
balance.
let's do spherical. Spherical is going to be a little weird because it's going to be rho squared sine phi, d rho, d theta, d phi. We got a little problem with rho. Theta and phi aren't going to be a problem. Theta, in fact, is just 0 to 2 pi because that's the same theta as here. The phi we've already got figured out. It was the phi always starts on the positive z axis. My bad. The phi always starts on the positive z axis and then just leans. So it starts at 0 and then it leans and it's going to lean out. Well, it's going to be pi over 3 because that's half of the 2 pi over 3. Uh, the spherical, the rho is a little tricky here because um, it's actually if I draw a line through the origin coming out of the object, it's actually going to exit the object through the flat top. So its
The
lower bound is 0. Okay, that's not a problem. Okay, but up here we do have a little bit of a problem. And so it turns out that what we need to do, let me come down here. It's getting a little cluttered here. I need to make a picture that relates the uh, the row with the angle. So I'm going to draw a picture here, kind of a side view.
Can you scoot the paper up so we can
Yeah,
get
my bad. I'm sorry about that. So let me just make sure I get everything. This is z equals 1 over rad 3. And so it's actually, this unit here is 1 over rad 3. This is rho. And okay, so I have enough information here. Phi is this internal angle. Rho is this length here. So I've got a relationship here that I have a hypotenuse and an adjacent. And so that tells me that the sine, wait a minute, so that's cosine, my bad. Cosine of phi is going to be adjacent, which is the 1 over rad 3 over rho. Okay. And so I just need to solve for rho. And when I divide cosine, I actually get secant of phi. So it's going to be 1 over rad 3 secant of phi. Wow. All right. Because you can tell that rho is not constant. You know, it's going to change depending on your angle of phi. So rho is actually a function of phi. Okay. So these are the three setups. So my question to you is, which one looks the friendliest?
the cylindrical.
I absolutely agree. So I think the part of the learning here that you're part of the I guess the point of this problem is to see that if you set it up as Cartesian, it looks like a nightmare. Spherical doesn't quite, it'll work, but this is going to be trouble. Integrating secant. All right.
Yeah.
This will probably work, but it doesn't look like a whole lot of fun, even though 5 of the 6 bounds are constant. This guy right here, this one looks real friendly. I I I absolutely agree. This one looks like the friendliest of the three triple integrals. All right.
Perfect.
Well, it is 7 o'clock where I live. So we've been together
Yeah.
for an hour. I'm going to go ahead and power down here. I'll get this thing up on the YouTube channel in about an hour. So I'll be sending out an announcement to everybody, uh, letting them know that this is available. Also reminding people, put questions on ed discussions, and also start doing the uh, test 3 practice now. I noticed a lot of people waited until the last moment. You want to start doing the practice 3 test soon so you get some more practice. So I'll send a reminder out to everybody about that. All righty. So it was good to see you guys. I'm going to go ahead and power it down here.
Bye. See you next week.
See ya.